Assalamualaikum and good day everyone. Okay, so today we will continue on the chapter 2, double integrals. And the linear outcomes for this topic is first, when you have completed this topic, you will be able to evaluate double integrals over non-rectangular regions, which we have discussed this on our last lecture. Second is you will be able to change the order of integration for non-rectangular regions and find the area of the region using double integrals. So for this lesson, so we will split into two parts, where the first part is for LO number 1 and 2, and second part is LO number 3. So this is double integrals over non-rectangular region. Okay, so we have discussed this before. Okay, if we have x where the limits is from a to b and y is from g1 to g2, so we can have the double integral of fxy dA, where dA is dy dx, and the limits of y is from g1 to g2, and for x is from a to b. Okay, meanwhile, if we have y is from c to d, so we will have the integral which is dx dy, where we have dy, or the limits of y is from c to d, and the limits for x is from h1 in terms of y and h2 in terms of 2. Alright, these examples also we have discussed before, where these two questions give the same answer. Okay, so as a conclusion for non-rectangular region, we have type 1 and type 2, where type 1 is we have the limits of integration of x is from a to b, and the limits of integration for y is from g1 to g2. Okay, so we have the type 1 and the type 2. Okay, so how to find the limits of integration, and then we need to solve the integration. So the first step is to sketch the region bounded and label the bounding curves. Step 2 is to find the y limits of integration. Step 3, find the x limits of integration. And step 4 is to solve the integration. Okay, let's look at this example. Sketch the region of the solid whose base is the region in the xy plane that is bounded by the circle x squared plus y squared equal to 1, and the line x plus y equal to 1, while the top of the solid is bounded by the plane z equal to fxy, which is equal to 4x plus 2. So let's just sketch the region. So actually this is the region where we have x squared plus y squared. Here is actually a circle with radius 1. Okay, and another equation, we have x plus y equal to 1. So we have y-intercept at 1 and x-intercept at 1 also. Then we have just a straight line here, over here. Okay, so we will have the graph, or the shaded region is over here. So this is step 1, where we need to find, or we need to sketch the region. Step 2 is to find the y limits of integration. Okay, so we have just now the region here. This is the region. Alright, to find the limits of y limits of integration, so what you need to do is you just draw a straight line, okay, parallel to y-axis. Okay, so have a straight line, or maybe this is just an arrow. So this arrow will touch the first point in the region where the equation here is x plus y equal to 1. And from this equation, we can rearrange and we will have y is equal to 1 minus x. So this one will be the lower limit. And if we use this line, this straight line, and it will end here, and here is the point at x squared plus y squared equal to 1. And from this equation, we can rearrange as y equal to 1 minus x squared, and we have square root here. Okay, and here this will become the upper limit of y. Okay, next. Step 3 is to find the x limits of integration. Right, so we have here the x-axis, and the x-axis, okay, from the x-axis we can have the region here, okay, is from 0 to 1. Okay, if you want to find the integral of dA, where dA is dy dx, so the limits of dy dx must be a number. That's why we only have from 0 to 1 as the limit of integration for x. We cannot have an equation for x limits. Next, we move to the final step, which is to solve the integrals. But before we solve the integrals, so we need to put all the y and x limits of integration. Okay, so just now we have the y limits of integration. The lower limit is 1 minus x, and the upper limit is square root of 1 minus x squared. And for x limits of integration, so lower limit is 0 and the upper limit is 1. Okay, next we can solve the integration. Okay, so actually to solve this equation, you need to use the substitution method. Okay, so just now we have the integration of dy dx. So actually we also can have the integration as double integral fxy dx dy. Okay, so if we want to have the dx dy, which means that we need to find the new x and y limits of integration. Okay, so first let's start with the x limits of integration, because here is dx, so we need to have a function here. Okay, functions in terms of y, right? So how are we going to find the limits of integration? So here is dx, so what you need to do is draw a straight line, okay, which parallel to the x x-axis, and the line must across the region. So this is the region just now, the same region. Okay, so this is the line which across the region. Okay, so from this line, okay, we can see that it first touch this line or this point, and this point is actually on the line of x plus y equal to 1, and therefore we can rearrange the function as x equal to 1 minus y, because we want to find the limits of integration of x. So that's why we need to have an equation where x is the subject. Alright, okay, next let's continue the line here. Okay, and this straight line will end here, and this point is actually on the curve or on the circle x squared plus y squared equal to 1. And from here we can have x equal to 1 minus y squared square root. Okay, so we will have later, this one will be the upper limit, and this x equal to 1 minus y will be the lower limit. Okay, here this is upper limit, and this is the lower limit. Okay, so alright, so settle for the x. So now we're going to see the limits of y. So since y is the last things that we need to integrate, so here you need to have a number. Okay, the limits of integration for y is just a number. So what are the numbers? Okay, what is the lower limits and what is the upper limit for y? So we have here, this is our region. Again, here is the region, and the region here is between, okay, y between 0 to 1. So y will become the lower limit. So y equal to 0 will become the lower limit, and y equal to 1 will become the upper limit. Okay, so we have here y equal to 0 and y equal to 1. Right, so we have the integration here. Again, you can solve the integration. Let's look at another example. Find the volume of the solid that is bounded above by the plane z equal to 3x plus 1 and below by the region enclosed by the parabola y equal to x squared and the line y equal to 2x in the xy plane. Okay, here we have, from the question, we have 3 equations. Right, and the keyword here is to find the volume. So the volume formula by using double integral, so we have double integral fxy dA, where dA can be dy dx or dx dy. So we will discuss both. Alright, so from the equation, okay, we have first equation is z equal to 3x plus 1. So we have, okay, before this, we will have z equal to fxy. So here we have the fxy. So the fxy just now, you just replace with 3x plus 1. Okay, so So the function of z just replace in the fxy here. Okay, so now we need to consider, or we need to find the limits of integration here. Okay, so we have the equation which is y equal to x squared. Okay, this is a parabola. Okay, here we have like this. Okay, and we have another equation which is y equal to 2x. So this is just a straight line. Okay, when we combine these two equations, okay, we will have the region. So here is the region. Okay, and we have the intersection point here. Okay, this is 2, 4, means that here you have 2 and here is 4. So how are you going to find these two? Okay, from where you get these two actually? So this one is actually the intersection between these two equations. Okay, so you will have x squared equal to 2x. So if we rearrange, so you will have this one, x squared minus 2x equal to 0. So factorized, so you will have x minus 2 equal to 0. So this implies that x equal to 0 or 2. So that's why you have here x equal to 2, and over here is actually x equal to 0. Okay, alright. So we have the region. Now you need to find the limits of integration. Okay, we start with dy dx first. Okay, if you want to have dy dx first, so you need to draw the straight line, okay, which across the region, okay, and parallel to y-axis. Okay, and then from that line, okay, we will have the lower for y limits of integration, which is y equal to x squared, and we have the upper y limit, which is y equal to 2x. Okay, so this is the y limits of integration. Okay, so we have settled for the y. What you need to find is the limits of integration for x. So you can see that, okay, the region here, okay, is from x equal to 0 to x equal to 2. So x equals to 0 will be the lower limit, and x equal to 2 will be the upper limit. Okay, and therefore we will have this double integral, okay, where y is from x squared to x, okay, and dx is from, or x is from 0 to 2. Right, so this is the integral that we need to develop. Okay, since the question asks you to find the volume of the solid, which means that you need to solve the double integral. Okay, and this is the solution. Okay, you just integrate as usual. Okay, first you integrate with respect to y, and then substitute the values of upper and lower limit here. Okay, and then we have the function in terms of x only. Okay, simplify it, and you have the new function which all is in terms of x. Okay, so here you need to integrate with respect to x, and you will get the integration here, and what you need to do is substitute the upper and lower limit, and you will get the final answer is 60/3 unit cube, since this is the answer for the volume of the solid. Okay, so just now we have the dx dy. So if you also can find, or you can also use dx dy to solve the integration. Okay, so let's try to change it to dx dy. So dx dy means that you need to have v equal to double integral, okay, f x y dx dy. Okay, the same region here, where you have here 2 and here is 4. Okay, clearly we have here y is between 0 to 4. Okay, so we can put the limit for y is from 0 to 4. Okay, now the problem is to find the limits of x. So to find the limits of x, you draw a straight line parallel to x-axis, okay, but it must across the region here. Okay, so we have this as the lower limit, okay, and the lower limit here is from the equation y equal to 2x. And since we want to find x limits of integration, so you need to rearrange. So x equal to y over 2. Okay, so this is the lower limit, y over 2. Okay, now let's look at the upper limit here. So this is the maximum, okay, or this is the largest value. So it's come from the curve here. Okay, this is y equal to x squared. So y equal to x squared, so we need to rearrange so that you can have x equal to square root of y. Okay, so x equal to square root of y becomes the upper limits of integration. Okay, so we have here v equal to double integral fxy dx dy, where x is from y over 2 to square root of y, and x is from 0 to 4. Okay, so actually if you solve the integral, okay, you will have the same answer. You can try it later. Okay, so this is an exercise, okay, that you can try solve it. Okay, we have the function dx plus y squared, and we have here dA. So we do not know the limits for the region, and this dA can be dy dx or dx dy. Okay, so what you need to do is draw the region or sketch the region. Okay, given to you in the question is evaluate double integral to x plus y squared dA over the region R in the first quadrant. Okay, first quadrant means that you have this one. Okay, this is the first quadrant. Okay, so it's bounded by, okay, bounded by the axis. Axis means that you have this axis means you have x-axis and also y-axis. So this is x-axis and this is y-axis. Okay, it's bounded with these two lines, and it's considered as in the first quadrant, and we have the equation y squared equal to 1 minus x. So what is the graph of this equation looks like? Okay, maybe you can rearrange this one. Okay, this one will becomes x equal to 1 minus y squared. Okay, so 1 minus y squared, we have minus here. Okay, and this is y squared, so basically I think negative y squared, you will have somewhere like here. Okay, and this is negative y squared, so you have 1 here, so actually I think you will have like this. Okay, where this one is 1. Okay, so the region bounded by the first quadrant and this function and the curve here, so actually this one is the region. Okay, so when we want to put in the integral where we have dA as dy dx, okay, clearly here you'll have x between 0 to 1. Okay, and for y limits of integration, so this is y-axis, so just draw a straight line. Okay, parallel to y, and we have here as the lower limit and this is as the upper limit. So we have the equation y equal to 1 minus x. Okay, square root of 1 minus x. Okay, so here the limit is y minus x. Okay, so you may proceed with the integration. The practice exercise, so you can try to solve the exercise. Okay, that's all for this part, so we will continue on the second part later.